Hey guys, so section 11.2, we're going to be doing goodness of fit tests. What this basically does is we're going to be able to run multiple proportion tests at once into a type of chi-squared. So this is going to be a type of chi-squared test. We'll have two, 11.2 and 11.3 are both chi-squared tests. But for this one, what we're going to do is we're going to have to start with, the same PRTC. So we're going to start by defining the parameters, and we are dealing with proportions. So it'll be P is equal to the proportion of blank versus or over or whatever. So in this situation, 379 randomly selected birth records were obtained, and the frequency distribution is listed in the table below. We have the number of births versus the day of the week. Okay, so this has multinomial, multiple terms, and our proportion is the number of births versus the day of the week. And we have 379, so that's our total sample size. All right, so what are the requirements for this? Well, we need to have basically the requirements for a proportion. The trials must be a fixed number of trials. Okay, the trials are independent. They must be only put into several categories. So Sunday, Monday, Tuesday, Wednesday. This is kind of a little confusing, but basically this is going to have only one set of values during the days of the week, just versus the births. If we had births and something else versus day of the week, then we would not be running this test. We'd run the next test. But so you have to basically have one category, and the probabilities must remain constant. So over each trial, the probability of having a birth on Monday or Tuesday or Wednesday, they are independent, and that doesn't change. Just because somebody has a baby on Monday doesn't affect somebody else's chance of having a baby on Tuesday, Wednesday, Thursday. Okay? This is called the goodness of fit, because basically what we're going to do is we're going to test how well this data, once again, this data right here, goes against some claim. So I'm going to go ahead and keep moving on this, but you need to make sure that you type this data into column A. Okay? So, and that's going to be called our observed data. Now, I've already done that, so like I said, feel free to pause and kind of type those in. I like to label this OBS, but you'll see as we go, I got to kind of come up with new names as we go. But these are our observed data points. Okay. PRT, we're going to be running a test. So the test is called a chi-squared goodness of fit. Or GOF, they'll do that. Okay. That chi-squared, I know it looks like an S, but we're not, or an X, but it's not really an X. So this X chi-squared is basically this CHI. So chi-squared, kind of like your T. It's like a cursive X, but it's a chi. Okay. The hypotheses here are basically that P1, we have two options here. Either they're going to claim, so whatever they claim, they're either going to claim that all the proportions are equal. So however many there is, so of the number of categories, I guess. And basically, they're basically either going to claim that all the proportions are equal, or they're going to actually give us amounts that they claim, where we're going to say like P1 equals some number, P2 equals some number, P3 equals some number, and so forth till we get to the last category. And that's basically that all the proportions equal whatever claim has been made about them. Okay? So we're going to start by assuming not just that one proportion is equal, but that all the proportions are equal, or all the proportions are equal to an amount that's claimed. Alternatively, what we're going to do is we're going to try to prove that at least one proportion differs. So I'm not trying to prove that all of them are different. I just want to prove that at least one of them differs. Okay? When we do this, we're going to calculate a chi-squared value. And that will be by doing observed minus expected squared divided by the expected. And that's how we get a chi-squared, and I'll kind of talk about that. From that, we can find a p-value by doing chi-squared CDF with our chi-squared value as the minimum, the max forever, and degrees of freedom. And degrees of freedom will be the number of categories minus 1. Okay, not the sample size, not how many people, but how many categories do we have minus 1. So chi-squared, let's see, 9999, k minus 1, that should be right. I'll double check as we go. What else do we need? We already said we need to make sure we list degrees of freedom. And from that, compare it to an alpha, we should be able to write our conclusion. Okay? So let's go ahead and go through. Let's find the chi-squared. I've already, like I said, typed the list 1 in. Let me figure out what the claim was in this example. I don't want to go too far. They said, I don't think they said. So I'm going to say, that the births occur with equal frequency. So basically, our null hypothesis this time is going to be that the proportion of Sunday equals the proportion of Monday equals the proportion of Tuesday equals the proportion of Wednesday equals the proportion of Thursday equals the proportion of Friday equals the proportion of Saturday. What? That all the proportions are equal. That the proportions of births were equal over each day. And alternatively, at least, L-E-A-S-T, one proportion differs. Okay, so that would be, for this test, how you do that. How do we calculate the chi-squared? Well, we already have in our table, we already have, there we go, the observed. What we have to do is we have to figure out the expected. Well, we said the proportions would be split up equally over 7 days, and there were a total of 379 births. So if I take that 379 and I break it up evenly, divided by 7, then we should have our number of births. We would expect that to be spread out evenly. Now I understand nobody's going to have 54 point whatever births, but the idea is that this is going to give us that number spread out equally, which is what we're testing against. So we can take each of these. So to get the chi-squared, we're literally going to take every single one of these observed values, 36, 55, 62, and subtract the expected. So let me see if I got some space here, okay? So I'm going to do this right here. So our first observed value was 50, or 6, no, it's up there. So 36, 55, 62. So 36 minus what was expected was the 54.1429 squared divided by the expected. This is almost like thinking like a z-score. We're finding out how far away what we observe is from what we would expect to be if the claim were true, and then by dividing it by the number of expecteds, we're finding out almost how many expecteds we are away for this one. Okay. Oh, I forgot something on my formula, because I know I'm about to do this. Where was it? Observed minus expected squared. I'm sorry, I know you're all probably upset at me right now, but the chi-squared is going to be the summation. So we're going to add up all of these one at a time, okay? So the first observed minus expected squared divided by expected. The second one was 55. So plus 55. Plus, I think the next one was 62 minus, divided by the expected, plus, and I'll look at my calculator real quick. After 62, that's convenient, 2 60s, a 58, and a 48. So 2 60s. Plus the other 60. Plus, I want to say 48, but I don't want to get myself in trouble. Alright, what was it? 58, then 48. Alright, so then 58. And then what was it? 48. Squared divided by. Okay, now this is going to give us our chi-squared value. So let's go ahead and do that. I'm not going to do each of these manually. We know enough about our calculators to do this. I'm going to take everything in A minus everything in B, square it, and divide it by the expected. You can even use the names, but I'm going to go ahead and just put, so hit enter here, should be an equal sign. Everything in A, parentheses, A, bracket, minus, anytime now, minus, B, bracket, squared, that's observed minus expected squared, divided by the expected, which was in B. So that would be divided by B, bracket. If I hit enter, these are all of our chi-squared values. This one was about 6, expecteds away. This one was 0.01, expected 1.14. This is kind of like a z-score, not exactly, but it's just a way of thinking about it. But I'm going to take all these, and to get the chi-squared, we're going to add them. So I'm going to cheat here rather than running one of our stats. I'm going to put an equal sign. Maybe. There we go. Put an equal sign. And I just want the sum, S-U-M, of everything in C. Of C bracket. And that is our chi-squared, 9.4723. Alright, how do I get the p-value from that? Well, the way a chi-squared works is it's a distribution. Because it's chi-squared, it's all positive. So it starts at 0, and it goes to the right, and it is skewed. Okay? So we're basically going to go to 1, 2, 3, 4, 5, 6, 7, 8, 9 standard deviations and calculate the probability of being there or further. So it's always to the right. So to get the p-value, we do chi-squared CDF, that 9.4723, infinity, and degrees of freedom. How many categories are there? How many days of the week are there? 7 minus 1, 6. I'm going to do that on the scratch pad here. So where was it? Chi-squared, menu, statistics, distributions, chi-squared CDF. Our lower bound was the 9.47, I want to say 27, 9.4723. All right. Upper bound, a bunch of 9s. Degrees of freedom, 6. Our p-value is 0.1487. So 0.1487. And they said the alpha we were using was what? The alpha we were wanting to test against was 0.5. So we can conclude that since the p-value is greater than alpha, we what? Same thing we've done on every other one. We fail to reject that. Now I can write P1 equals P2 or PM equals PT, or just write in words all of the proportions are equal. We do not have evidence that all of the proportions are equal. Okay? Alright. That was a lot of work. We got 2 more of these. Wouldn't it be nice if your calculator would do this for you? Here's some good news. Observed, expected. We have our results so far in D. So I'm going to go ahead and do menu, statistics, tests. Wouldn't that be great if there were some chi-squared tests in here? That looks like a chi-squared test. In fact, it has the GOF, goodness of fit. Where was our observed? Our observed was in A. The expected we put in B. And degrees of freedom, category 7 minus 1 is 6. And the results, I think, in E are fine. Is that the same chi-squared value we got? Is that the same p-value we got? Isn't that convenient? What is this little comp list? That's actually pretty cool. 6.0795. Look at this top number, 6.0795. Look at the second number, 0.0135. Look at this second number, 0.0135. This list right here is all of the chi-squared values separated into one list, and then this is what? The sum of all of those together. So this is actually pretty fancy. It's kind of nice that it does that. And what's amazing is it does what? It takes every observed, expected, squares them, divides them, adds them, calculates the p-value, and spits out the display in less than a second. I think that's pretty fancy. Alright, so let's try again. Let's do another example. Radio station claims music preference of the listeners in the station's broadcast region are distributed as shown in the table below. You randomly select 500 music radio listeners from the broadcast region and ask each which type of music he or she prefers. Using an alpha of 0.01, test the claim to observe that the observed frequencies agree with the claim distribution. Now this one's different, right? Because they're not trying to say all of them are equal. They're saying that only 4% of the people they claim like classical, 36% like country, God help them, 11% like gospel, 2% like oldies. So when I set up my P, this is going to be the proportion of, people, observers, who prefer, and you could list them all out, but we just say the different types of music. Okay. What are our requirements? This data must be collected. It says randomly, so that was stated. Second, we need independence. We need the probability to stay the same over each trial. And I need there to only be one category across, which there is. Okay? So do the SRS. The rest of them we can talk about, but this is not an A-basket issue for me. Yes, I still want you to list them and know them, but we've been checking requirements for a long time now. This is really old hat. Okay? So PRT, we're going to run the test. Which test? chi-squared, goodness of fit. Well, I see the observed. I hope you do too, right? The survey results are what we actually observed. OBS, okay? We need to figure out the expected. You're like, well, that's the 4%. No, it's not, right? The 4% is what we expect out of the 500 people. 4% of the 500 people. So we have to calculate the expected. Excuse me. By taking the total times each probability. And so on and so forth. So it will be 500 times 4% would be 20. So for classical, we would expect 20. For country, 36%, I believe, would be the 180. 11% should be 55. 2% of 500 would be 10. 18% would be, is that 90, I believe? And 29% would be 145. Double check, that should add up to 500. So let's see. 200, 255, 265. Yeah, I think that's 500, so I'm feeling pretty good about this. So those are our expected values, okay? You have to put this in the calculator. You need to list the observed, you need to list the expected. I've already put in the observed, so that was the first numbers. That's our, I guess SR, I don't know why I put that, survey results, and this will be our expected survey results, assuming everything met what they had claimed. What were our numbers? 20, 180, 55. So 20, 180, 55. And 10, 90, 145. How am I going to do this test? Not by hand, not doing every observed minus expected squared. I'm going to let the calculator do some heavy lifting. Statistics, tests, chi-squared, goodness of fit. Our observed results are in. How about A? Oh my gosh, come on. Forget it. A bracket. Our expected was in B. Parenthesis, bracket. Degrees of freedom. How many different music types did we have here? 1, 2, 3, 4, 5, 6 categories. So our degrees of freedom will be 5. Put the results in C. Okay. I'm about ready to write a conclusion on this. Here's what we'll do. Mail it PRT. We didn't write the hypotheses yet. Our hypothesis should be that P1, which was what? Classical, is 4%. P2, 36%. P3 is 11%. P4 is 2%. P5 is 18%, 0.18. P6 is 29%. So basically each of these equals the claim proportion. Alternatively, at least one differs. Okay, we got our degrees of freedom. We have a chi-squared value now. Let me see. Chi-squared was, I lost it. Let's go up here. 22.71. We have a p-value of 0.0004. And that p-value is way less than the alpha of 0.01. So in conclusion, since the p-value is less than alpha, we reject that the proportions equal the claim and conclude at least one differs. Okay? Which one? Which one do we think differs? That's actually kind of cool, because once you have this, I can look at my calculator. Remember this comp list? Which of these has the biggest chi-squared value? I see a 7, a 5, a 5.2, a 0, 2.5, and 2.7. That 7.2 is the biggest. This 8 was the one that was the furthest away from what we expected. So you can look at the chi-squared values, find the largest one, and that actually tells us. So as much as some of you are looking at this going, oh my gosh, this test is a lot of work. Well, keep in mind, we basically just ran 6 proportion tests in one. We were able to compare all 6 of these proportions like instantly to some claim and figure out that which one should I maybe run a test on that I think is different from the truth. Well, that one's the one that's different. So this is a quick way of basically running. I could do proportions of the days of the year. I could run 365 proportions at once using a chi-squared test instead of having to run a one proportion test 365 times. See, that's the beauty of this test. And last but not least, social service worker believes the marital status of mothers receiving food stamps is uniformly distributed. That's important. So equally, right? Test this claim, you randomly select 101 mothers. Of course, it's an odd number of mothers who currently receive food stamps and record the marital status of each at an alpha of 0.0025. Can you reject the claim that distribution is uniform? What is this frequency? They randomly selected 101 mothers. This is what we observed. For full credit on this, you don't just do the expected in your calculator. I'm going to want you to list the expected. So what is the expected? Well, 101 divided by 4. So 25.25. Okay, so once again, let's go ahead and start with the P. What are we dealing with? The proportion of mothers receiving food stamps versus marital status. What are the requirements? Verify the data was collected randomly. Verify that there's independence. This one being married with a husband doesn't affect this one whose husband's gone. Okay. Verify we have only one category, and what was the other one? Oh, that the probability stays the same. Okay. So PRT, we're ready to run the test. What is our test? Chi-squared, goodness of fit. We got the observed, we got the expected. Okay? Take a minute, type in the observed. I call them frequency and expected frequency. It's these numbers, and then it's 20.4101 divided by 4. The calculator can do some heavy lifting for you. Okay, that's the hard part. Filling in the observed, filling in the expected. The calculator will do the heavy lifting from here. Stats tests. Where are we at? Chi-squared. Goodness of fit. Our observed was in A. Our expected was in B. Degrees of freedom. Get me in trouble here. Where were we? Okay. 1, 2, 3, 4 categories. So 4 minus 1, 3. We'll need a chi-squared value. We'll need a p-value. Degrees of freedom, what did I just say? 3. Okay. And we got a chi-squared of 9.238. And a p-value of 0.026. Okay, so what does this mean? Well, our alpha was 0.025. So, conclude that p-value is greater. So we could say, since the p-value is greater than alpha, even slightly, we would fail to reject that what? That the proportions are, we never put a hypothesis. So you get me in trouble here. P1 equals P2 equals P3 equals P4. All the proportions are equal. Alternatively, at least one proportion differs. Okay? Since the p-value is greater, we fail to reject that all the proportions are equal. And if we reject that, we conclude, oh, no, we didn't reject it. We're done. So, kind of, the beauty of this test, again, I mean, this just saved me from running 4 proportion tests, I get that. But it is basically, highly sensitive to any of these numbers being really far off from what we expected. So let me show you what I mean, because these all were off by a little bit, but they weren't off enough to kind of, ding the bell of what we expected here. So what if I just took, let's go ahead and go to our data here, and instead of being 20, 19, and 23, I'm going to take 10 of these people right here, and I'm going to stick them in the second group. So I'm going to make that one 10, and I'm going to stick them here. What happened here, right? Well, our chi-squared got a little larger, but our p-value got substantially smaller, right? And if you look, the first one's 5, the rest of them are like small. The rest of them are not too far off, but that 5 right there, that one being really far off, kind of rang the bell of the chi-squared test and said, hey, one of these is off. One of these is far enough off. At least one of these is really far off enough that we think that not all these proportions are equal. Okay? So that's what the chi-squared does. If any one of these gets really far off from what we expect, then the chi-squared and the p-value kind of get all excited and rocket off and go, whoa, we got an issue here. This is not what we expected. So that should be it for the chi-squared. Let me double check if there's anything else. I don't think so. So keep in mind this can occur in a few ways. All the proportions are equal, which is nice, where you just kind of set them equal, or if they give you a claimed amount and you got to calculate it. For each question on the test, I will expect you to have the observed and the expected listed. Just list them next to each other, and that'll be fine. Okay?